Alright, so hello everyone and welcome to Rasayan Academy. So today again we are going to talk about the 2-mark questions basically. Alright, and I have already told you that I'll be making two playlists separately for 2-mark question as well as 4-mark question for the CSIR NET as well as a GATE exam practice. Alright guys, so let's begin with it. Okay guys, so my name is JAGRITI Sharma and I'm an educator on the Unacademy Plus platform. So guys, as I've already informed you that if you visit my profile, you'll be able to see the special classes that I'm taking, which are basically free live sessions. The special classes are free live sessions, and if you follow me, you will definitely get regular updates about my upcoming courses. Okay. So first of all, let me quickly tell you about my Plus courses. So what is a Plus platform, guys? It is a paid platform. Okay, and I have already made a separate video describing that how to access a Plus platform and how can you gain maximum benefit from the Unacademy Plus platform. There is a different video, and I've also told you about my upcoming courses from the month of January till March. Okay, so the whole plan I have given you from January to March, and from April to June, let's say, we'll be doing a lot of revision and inorganic chemistry as well as practice sessions. Okay. So these are the upcoming courses on organic chemistry basically. I'm having a batch course as well as an individual course. So I'll be sharing a lot of content with you guys, and this is my code JAGRITI S, and the referral code is used for a 10% discount in whichever subscription package you want to have. Okay. Alright guys, so let's now begin with our questions for today. So the first question is, the decreasing order of reactivity towards an electrophile is. So we are given three options, and the question is asking about the decreasing order of reactivity for these three compounds. We are having pyrrole, we are having thiophene as well as pyridine. So it's a very plain question guys from the GATE exam exactly, and what you have to do is you just have to consider the reactivity towards an electrophile, which means since all of them are aromatic, so it is going to be electrophilic aromatic substitution. Now I would suggest you to stop the video, and I've already given you this hint. Try this out by yourself, and then we will resume. So alright everyone, I hope that you have tried it out by yourself, and let's start answering this question. So basically the reactivity of towards an electrophile is going to give us electrophilic substitution reaction. Okay. So what do we see? If you have already studied the electrophilic substitution on benzene, then you know the mechanism that it is the benzene is going to attack over the electrophile through a pi bond, and it is going to give a sigma complex in turn. It is, for example, I have attached the electrophile over here. It is going to give us a sigma complex like this, and the proton will be taken up by a base or by the medium itself to give back the aromaticity. This is called the rearomatization step. So this is the overall electrophilic substitution reaction. But what about the heterocycles? These heterocycles are a bit different from benzene. So definitely they are having different resonance energy as compared to benzene. Definitely the reactivity will be different. So I have already explained it in the next slide basically. Yeah. So the question is asking which heterocycle best undergoes electrophilic substitution reaction. That is going to come first. Basically we are going to arrange in the decreasing order, right? So let's see. I've drawn the mechanism for all of the heterocycles reacting with the electrophile. So let's first consider pyrrole system. So guys, as you can see, the lone pair on the nitrogen can be included into the 5-membered ring, which is making it very electron rich, and that is why it can attract the electrophile very easily like this. Okay. Also the intermediate, the sigma complex is going to be like this, and it can give back the pi bond can fall over here, or let's say it can fall over to this side to give back the electron density on nitrogen. So this is how we are getting our substitution. So if you have studied about the aromatic heterocycles, then you would know that the substitution, basically electrophilic substitution on pyrrole, takes place on 2 and 5 position. So this is our second. So this is our 1, 2, 3, 4 and 5. So basically on these two positions, the electrophilic substitution is best for pyrrole. Moving forward, we see the same reaction for thiophene. So guys, again the sulfur is also having the lone pair, so similarly it is going to assist the attack on the electrophile on the same 2 and 5 position. So this is our substitution. Alright, what about pyridine? So pyridine, first of all, is the lone pair of nitrogen is not involved in resonance, so it is not increasing the electron density of the benzene ring, basically of the 6-member ring. Also, it is showing -I effect, because if it is not donating, then because of electronegativity, it is taking back the electrons. So the ring will be deactivated towards electrophilic substitution. Also, for example, let's say I am already writing this. Then what would happen? If I am already writing this mechanism, then the electrophile can attack on the 2nd position or on the 4th position, something like this. Okay. So what would happen? There would be a positive charge on nitrogen like this, and the positive charge which is on the nitrogen is definitely not stable. Also the resonance, or let's say there is not a much more stable system. First of all it is already deactivated, and then there is positive charge on nitrogen. It's making the system very unreactive and not stable. So we can say that pyridine is going to be least reactive. It is going to be least reactive of all of them. So when we are going to write it in decreasing order, definitely pyridine stays at last. What about pyrrole and thiophene? Because we have to maintain an order over here. Okay, so guys, the energies, basically the resonance energies of thiophene is 29 kilocalorie per mole, which is greater than that of pyrrole, which is 21 kilocalorie per mole. So what do you get from these values? Basically, the greater the resonance energy value, lesser is the reactivity, we can say. Okay, so because it is a more stable and less reactive system, so that is why we can say pyrrole is more reactive than thiophene. So 1 is greater than 2, which is greater than 3. Okay, so greater the stability, lesser is the reactivity, and that is why we can say pyrrole is more reactive. Alright, so our answer is going to be 1 is greater than 2, which is greater than 3. So D is our correct answer. I hope that you are getting my point. I hope that you have tried it out yourself as well. Okay, so now let's move on to the second question. What is the decreasing order of nucleophilicity of the following anions? Okay, so this is the whole question. Alright, just try to answer it yourself and then go on to the explanation, guys. So alright, so basically the order of nucleophilicity is definitely going to be determined by how much the lone pair, or let's say the negative charge, is available on the donor atom. So if we are talking about oxygen, how much charge is localized on the oxygen atom is going to determine its nucleophilicity. Okay, so let's see. In carboxylate anion, the lone pair, basically the negative charge is delocalized and it is giving two structures basically. Right, the carboxylate anion is giving two structures. If we talk about methoxide anion, right, so this methoxide, the oxygen is definitely, the charge is localized on oxygen, so we can say this is going to be more nucleophilic than the acetate ion. What about phenoxide? So similarly, guys, the phenoxide also has a lot of resonance structures. The negative charge will be included into resonance, delocalized, not much localized on oxygen, so it is going to be a very bad nucleophile. Okay, so we can say till now that this is our best, the methoxide is the best nucleophile, right? So we can give number 1 to this, number 2 to our acetate, number 3 to our phenoxide. What about nitro, or basically nitrate? Alright, so it is going to be something like this. Okay, there is a positive charge on nitrogen. So definitely, guys, it is also having a lot of resonance structures which are also identical. So 3 or 4 resonance structures which are also identical. So we can say it is also going to be less nucleophilic as compared to the phenoxide ion. Okay, alright, also we have one more method of explaining the same thing. Okay, so first of all, we are all having we are having the oxide bases. Basically the negative charge is there on the oxygen. So what we can do is we can do one more thing, that we can consider the acids basically. Okay, so we can consider the corresponding acid, then we will also be able to specify that which is going to be the best base, and the basic character is also going to be similar to the nucleophilic character. Why? Because over here we are having all of the donor atoms are oxygen, so we don't have to compare between the basicity of different atoms. All of them are oxygen, right? And that is why it will be very easy. So if we are able to understand the acidic property of all of the acids with corresponding acids for these anions, so basically we started from acetic acid, and then we saw a methoxide ion which can come from methanol, similarly phenoxide ion which comes from phenol, and nitrate ion which comes from HNO3 basically. Okay, so right now we know that the stronger is the acid, basically stronger is the acid Ha, weaker is the conjugate base, isn't it? So if it is very strong, then the conjugate base will be very weak. This is one more concept. Okay, so if we are considering about the nitrate anion, so guys we were a little confused about nitrate ki nitrate ka kya hoga, baki to sare organic hai, this is inorganic, right? So we were a bit confused. By now taking the acidic property, now considering the acidic property, now it becomes very clear. Stronger is the strongest is our nitric acid, right? So this is going to be the weakest base. Alright, this is going to be the weakest conjugate base. Alright, now what happens? Now it comparison between acetic acid, phenol and methanol becomes very obvious. So definitely methanol is the weakest acid, and that is why the methoxide ion is the strongest base. Then goes phenoxide, then goes acetate, and then lastly comes our nitrate. So this is going to be the answer, and the order of nucleophilicity is directly proportional to order of basicity because the donor atom is the same over here. Alright, so that is why we can say that our answer is going to be this one. Our answer is going to be option number C. I hope that this is a good concept, and I hope that you understood it. Alright, and guys, in my special classes and in my other sessions on Unacademy, we have solved a lot of such questions, and in the Plus platform we have solved around 200 to 300 questions in the last session. If you visit the Plus class you will know. Alright, so question number 3 is beta D glucose is represented as. So it's a very direct and simple question. You just have to identify the structure of beta D glucose. Okay, just that. So yeah, you can try it out by yourself. So usually what the D glucose molecule looks like is something like this. So the D glucose looks like this. Alright, yeah, it's over here only. Okay, so this is our D glucose molecule. So if it wants to form a pyranose ring structure, a pyranose ring structure is basically a 6-membered ring. Okay, so if it wants to form a 6-membered ring, then it has to attach to this hydroxy group. Okay, it is having 1, 2, 3, 4, 5, and the 6 would be the oxygen. So the 6th atom is the oxygen over here, so it has to form the hemiacetal of this oxygen right over here. Okay, so I hope that you have drawn the hemiacetal by yourself. Okay, and ultimately just it would be very easy for you to remember the structure of beta D glucose. It would be very easy if you do it that way. Okay, alright guys, so basically this is the structure of beta D glucose as I've shown, as I've already drawn. So it's a very easy way of remembering that in the beta D glucose, all of the OH group are equatorial, right? All of the hydroxy groups are equatorial. You look at the anomeric OH, this is also equatorial. About the rest others, this is on the second carbon OH, and this is our CH2OH. So we are not considering this one as equatorial. but the rest of the all hydroxy groups are going to be in the equatorial in the beta D glucose. So thermodynamically, considering energy wise, it is going to be the most stable system, right? And anomeric effect is different because of some different reasons. The alpha anomer is more preferred, okay, but thermodynamically we can say this is more stable. Now the thing is, why am I telling you to remember beta D glucose structure? Okay, because it would be very easy to answer direct questions like this. So over here you can see that in option number A, all of them are equatorial. In option number B, this one is axial, so definitely not going for that. Option D, both are axial. And option C, the anomeric anomeric OH is axial, which is going to give us the alpha D anomer. Okay, so our correct answer is option number A. So definitely you will be able to directly answer these type of questions. Along with that, guys, if I ask you about, let's say, what is the structure of beta D galactose? What is the structure of beta D galactose? Okay, so you must know what is the relationship between beta D glucose as well as beta D galactose. Okay, alright guys, so the relationship between galactose and glucose is that beta D galactose is going to be a C4 epimer of beta D glucose. Alright, so over here if we see, this is carbon 1, carbon 2, carbon 3. Alright, this is our 2, this is our 3, this is our 4. So the position of OH would be over here. Okay, so what we are going to do directly is, if let's say the conformation of beta D glucose is asked. Alright, let me just clear up a little bit from over here. So this is our beta D glucose, right? So over here what we can do is, we can just directly draw, we can remember that this was our beta D glucose, and we just have to change the position of the fourth OH group. And this is the first one. Basically this is the CHO group. The anomeric OH will be there on the first carbon. The second one is again equatorial. The third one is again equatorial. And the fourth one, this is our fourth carbon, right? So 1, 2, 3 and 4th, this is our fourth carbon. Usually it is equatorial, but if we are talking about beta D galactose, it becomes axial. Okay, so this is our beta D galactose. So this is how it would be so easy for you to remember. If once you remember beta D glucose, then you can just change the position of OH group in beta D galactose, which is a C4 epimer of glucose, as well as beta D mannose, which is a C2 epimer of glucose. Okay, so it becomes much more easier that way. Alright, so definitely our answer is option number A, and we are going to move forward to the next question. Alright, so the question number 4 is, toluene when refluxed with bromine in the presence of light gives. Okay, it's a very easy question, guys. So what will be the reaction of toluene in the presence of light with bromine? It's a very easy question, guys. It's a really easy question. So if you have already studied about the reactions of toluene, or basically it's a question from CBSE class 12. It is that easy. CBSE class 11, 12th question basically. So you are just going to get bromobenzene, right? So you are going to get substitution on the side chain. You are not getting any electrophilic aromatic substitution with Br2 in the presence of light. You are getting the substitution in the side chain. It's a very easy question. So you are not getting orthobromotoluene, you are not getting parabromotoluene, not even a mixture of ortho and para. You are getting benzyl bromide. It's that easy. So our answer is option number D. Okay. Alright. Now let me discuss one more thing. There was a doubt from last video when we were solving the ENE reaction. So I saw in the comments about some major confusion. So basically, guys, let me tell you one thing about the ENE reaction. The stereochemistry of the ENE reaction is different for acyclic systems. Basically, when we are not forming a ring over here after the ENE reaction, okay, and when we are forming a ring, then the stereochemistry becomes very important, okay, because in the 6-membered ring it can give a trans product, but in the 5-membered ring most of the times, or let's say for the 5-membered ring, maximum 6-membered product will be formed. Cis product will be formed. Why is that so? Let's see the transition state, what is happening. So usually you can find this type of a transition state for Diels-Alder reaction, for any reaction which is having a 6-membered transition state. Okay. Alright, so what did I do over here? Let's see, guys. See, first of all, this is our alkene system. Okay, 2 pi electrons, and this is our alkene, as well as there is a carbon hydrogen bond, and this is our 2 pi 2 sigma electron system over here. Okay, so what do we see? That this is how the ring closing is going to take place, and ultimately this is going to be our product. But what is the stereochemistry? Why cis and trans? Okay, why are we getting cis and trans? So for the 6-membered ring system, the very stable, or let's say very probable intermediate is going to be the 6-member transition state, something like this. So I have taken this bond I have taken over here. This is our carbon hydrogen bond. Basically this alkene is over here, right? And this whole group I have taken as R, and this whole group also I have taken as R. Okay, so I have not written the rest of the molecule over here for better clarity. So what do you see? If we draw a transition state like this, we see that one of the R group is above the plane. Alright, one of them is going to get above the plane, or basically we can just write axial, it would be better. Secondly, the other is going below the plane. Okay, and it is equatorial, but it is below the plane, as if we compare the formation of this bond basically. So this bond formation is actually this bond which is getting formed, and the hydrogen is transferred to the alkene which is forming the methyl. Okay, similarly the pi bond is going to come over here, this pi bond is going to come over here. Okay, so ultimately what do we see, guys? We see that one of them is going below the plane and the other is going above the plane. So we see from here very clearly, देखो, this is going below the plane, isn't it? This is going below the plane, this is going above the plane. So we see very clearly कि यहाँ पे जो geometry है, it is trans. And guys, the trans geometry is possible for a 6-membered ring system because this molecule can actually exist in a chair conformation, isn't it? And it is stable as a chair conformation, so cis and trans are possible for it. Okay, but when we talk about the 5-membered ring formation, when we are talking about over here, so the pi bonds are also going to move like this. Okay, it's a very simple moment concerted mechanism. So I have drawn the transition state for the 5-membered ring possibility as well, and as you can see, guys, देखो, I have drawn this alkene below like this. I have drawn this alkene above the plane because the system is going to be like this in the transition state. But let me tell you one thing, that it is not going to give the trans product, because if we make it like this, then the number of CH2 groups over here are less as compared to this one. Here we are having 1, 2, 3, 4. So definitely it is more flexible as compared to the 3 CH2 groups, which is making the ring more rigid. So it is making the ring more rigid and more less flexible basically, and that is why we can say कि it cannot stretch to trans. This is cis and this is trans. Okay, so it cannot just do that. ये जो है इस position में नहीं आ पा रहा है. That is why it is always forming a cis compound. The stereochemistry around the 5-membered ring is mostly going to be cis. Alright, because smaller rings cannot form trans geometry and cannot form a bond in the trans geometry. Okay, and that is why we can say that it is going to be, most preferably it is going to be cis. Okay, and the question was asked about major product. So I hope that we are clear on this. I hope that you will try more and more questions like this to clear this concept as well. Alright guys, so thank you so much for watching this video. I hope that you will like it. You would give it a big thumbs up, and you would also subscribe to my channel and also follow me on Unacademy for more such content. So guys, let me tell you that on Unacademy's live YouTube channel, right, there is a YouTube channel, Unacademy Live, from the Unacademy platform only. So right now for the next whole month of January, we will be discussing previous year questions from GATE chemistry. Okay, and along with that, today itself we are going to discuss about June 2019, December 2000, December 2019 exam paper, some questions, some analysis. Okay, that is what we are going to do basically. So I'll hope that you will show up, and if you follow me on Unacademy guys, you will get the link where you have to come up. Okay, so our session is going to be on 8:30 p.m. I think you will show up, and thank you so much for watching guys. I'll see you in the next video. If you are having any doubt, you can comment in the comment section below, and I'll try to clear your doubt in the next video which is coming up. Thank you so much guys.